Hello there and welcome back to The Sleepless Scientist. Tonight, you're drifting in a quiet void, just past the edge of everything. No ground, no sky, just an infinite silky blackness that stretches and folds around you like a bedsheet tossed into the cosmos. There's a weird stillness here, like the moment before a deep breath, and then something begins to move, not fast, not violently, but unmistakably. The fabric beneath you stretches. It's not space in space, it is space. And time, too. One fluid, flexible thing. A four-dimensional sheet you're smeared across like marmalade on a very confused crumpet. You float, but you're also falling and moving sideways in time and maybe even wrinkling slightly just by existing. And here's the kicker. You're not floating through this fabric, you are part of it. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Let me know in the comments where you're watching from and what time it is in your corner of the universe. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You open your eyes and what you thought was emptiness is now stretching softly in every direction. Not like a rubber band pulled to its limit, but like dough rising in slow motion. And you're not floating above it, you're in it. You're being stretched too, though you wouldn't notice. This is the truth about space-time. It's not just a background. It's not a stage where atoms and planets come to perform. It's the stage and the curtain and half the actors. And unlike most things in physics, it's allowed to move without anything pushing it. That idea alone broke physics for a while. But then along came Einstein, with his wild hair and even wilder math, and suggested that the universe's most sacred constant, time itself, wasn't so constant after all. He said space and time are stitched together into a single entity, space-time, and more than that, it could bend, stretch, twist. It's hard to overstate how weird that was. Before Einstein, people thought time just ticked forward, like a giant cosmic metronome keeping the beat, while space sat there like a big empty bucket. Newton's universe was full of invisible forces pulling and pushing things, but the fabric those things floated in, untouchable, immutable. A bit boring, to be honest. But Einstein didn't see the universe like that. He saw clocks that ticked slower near heavy things, rulers that shortened when you moved fast, and behind all of that, a fabric. One that reacts to mass and energy like a trampoline sags under a bowling ball. You might remember this one from every physics classroom ever, the classic demo with the stretchy rubber sheet. Drop a weight in the centre and watch how marbles spiral inward. It's a great visual, even if real space-time doesn't need a sheet or gravity pulling downward. It just warps on its own. And here's where things get cozy and unsettling. You're always inside that warp. Right now, lying wherever you are, the Earth is tugging on space-time, stretching it downward so that time ticks just a little slower for you than it does for someone on the International Space Station. Not by much, but measurable. GPS satellites literally have to correct for this effect, or your directions would slowly get weirder until you end up in someone's backyard instead of a coffee shop. You're constantly being curved just a bit. Your atoms are on a very slow roller coaster, and that's not even the dramatic stuff. Wait until we get to black holes, regions where the fabric gets so warped it folds in on itself like a crumpled napkin. But for now, let's stay here, in the gentle stretch. You look up, galaxies drift apart, stars wink out quietly, red shifting as they go. It's not because they're moving through space, it's because space itself is expanding. The very coordinate grid you'd use to measure distance is pulling apart. This stretching is everywhere, and yet, you don't feel it. Your body doesn't grow longer, your atoms aren't flying away from each other. Why not? Well, because gravity and electromagnetism hold you together. Your body's glued tightly enough that local space doesn't get a say, but out there, between galaxy clusters, that's where space-time gets to show off. Here's a fun little side trip. In the 1300s, a Persian astronomer named Qutb al-Din al-Shirasi guessed that the heavens were expanding. He was mostly wrong, but oddly ahead of his time. Historians still argue whether ancient stargazers might have noticed redshift without knowing what it meant. The evidence is sketchy, but the curiosity, eternal. Modern cosmologists now use phrases like metric expansion of space, which sounds like a bureaucratic nightmare, but really just means the ruler itself is getting longer. If you measured the universe yesterday and again tomorrow, you'd find it bigger. Not because the stuff inside it moved, but because the grid got stretchier. And here's the weirdest part. Nothing caused that expansion in the usual sense. It's not like a grenade exploded and flung things outward. The expansion comes from the shape of space-time itself. It's as if the geometry of the cosmos is allergic to stillness. One day, scientists realized that the universe wasn't just stretching. It was accelerating. Like a runner who gets faster after the marathon starts. That'll come up again when we meet dark energy, but for now it means that this slow, stretching yawn of a universe isn't slowing down. It's pulling apart more dramatically every second. What does that feel like? Nothing. You still need to take the trash out tomorrow, but deep beneath your living room carpet, space-time is curling, stretching, and shifting. That's your foundation. The floorboards of reality are flexible. It makes you wonder how much of your daily life is spent standing on something you assume is solid, when it's actually rippling ever so slightly beneath your feet. That's not a metaphor, that's space-time. You sit quietly inside the bend of something bigger than you can name. Above you, a dome of dark velvet sky pricked with stars. Beneath you, the invisible trampoline Einstein imagined, one so massive and perfectly stretched that you can't feel the sag, but you're living in it anyway. You think you're sitting still, but nope. The fabric is shifting, gently, relentlessly. Here's the thing. Space-time doesn't just exist, it reacts. It bends when mass enters the scene, it wobbles when energy dances across it, and, once in a while, it sends out a ripple that travels across the cosmos like a hello from a very large, very old friend. Einstein dropped this bomb in 1915. His general theory of relativity turned every Newtonian certainty into jello. What Newton thought was gravity, a force that pulled apples to the ground, Einstein reframed as geometry. The apple wasn't being pulled by Earth. It was simply following the curve in space-time that Earth created by existing. Mass tells space-time how to curve. Curved space-time tells mass how to move. That's the slogan. It sounds like something you'd find on a nerdy coffee mug, and you would. But it's also the fundamental truth of modern physics, and it means, wherever you are right now, your body is responding to curves you can't see. Imagine placing a bowling ball on a stretchy sheet. The sheet sags. Now roll a marble nearby. It spirals inward. Not because the ball's pulling on it directly, but because the surface is bent. The marble's just following the straightest possible path on a curve. That's how Earth orbits the Sun. No invisible hand is yanking us along. We're falling forever sideways through the Sun's space-time dimple. But now we run into a bit of a snag, because the rubber sheet model, while helpful, is also a tiny bit of a liar. See, when you use that demo, gravity is what causes the dip in the sheet. But in real life, gravity is the dip. There's no downward force pulling on the mass to bend space-time. It's the mass itself doing the bending, and that's the mind bender. The fabric reacts in place, without needing any external force. No stagehands backstage, no strings, no scaffolding, and this is where you have to let your brain get a little stretchy too. Because if you accept that space-time bends around mass, then you have to accept something even stranger. You bend it too. Yep. Your body, modest though it may be, curves the fabric of the universe ever so slightly. You're not just in the cosmos, you're affecting it. The floor under your bed is imperceptibly different because you're lying there. That's not poetry, that's physics. Granted, your warping of space-time isn't enough to ruin anyone's day, but get enough mass together, say, a planet or a star, and space-time begins to sag with some real drama. It's like the difference between a cat curling up on a blanket and an elephant jumping on the bed. And Einstein's math didn't just predict curves, it predicted something wilder, that space-time can move. Enter gravitational waves. This is where things get fun and also slightly absurd. Because until 2015, we weren't sure these waves existed. They'd been predicted for 100 years, but detecting them was like trying to hear a whisper from across the galaxy using a microphone made of lasers and hope. Still, scientists built it. A massive machine called LIGO, with arms 4 kilometers long, waiting patiently for the fabric of the universe to ripple just enough to nudge their lasers out of alignment. And then, boom, 2 black holes collided 1.3 billion light-years away, sending a shudder through space-time itself. Not sound, not light. A literal compression and expansion of the dimensions you live in. That ripple passed through you. You didn't feel it. Nobody did. But the instruments did. They twitched. They hummed. The whisper had arrived. Gravitational waves are proof that space-time is not just a background. It's a medium. Like water rippling after a stone drops in, the universe flexes in slow-motion shockwaves when something big enough throws a fit. Now, to be fair, these waves don't do much to your day-to-day. They're so faint that the one LIGO detected only changed the length of its arms by less than the width of a proton, which, to put it mildly, is insane. But it means the universe is alive with motion, silent, elegant motion that moves through the void like a cosmic sigh. Here's your quirky corner fact for the night. Before Einstein, a few physicists thought gravity might be a kind of pressure from invisible particles, pushing objects together, like shadow pressure. It was called Lesage's theory of gravitation, and it's been very politely buried in the physics graveyard. Still, it goes to show, people have always tried to picture gravity. Turns out the truth doesn't look like a push or a pull, it looks like geometry. Of course, not everyone agrees on every detail. Historians still argue whether Einstein's insights came as cleanly and nobly as his biographies suggest, or if they were messier, with more borrowed ideas, more dead ends, and a few strokes of luck. Like all genius stories, the truth is probably somewhere in the middle. Brilliant, yes, but very, very human. And so, here you are. A tiny blip on a gently bending surface standing on a planet curving space and nudging time, orbiting a star nestled in a galaxy shaped like a pinwheel, all floating through a void that hums ever so faintly with gravitational lullabies. You don't feel the bends, you don't hear the waves, but you're part of them, always have been. You're not floating on the fabric, you are the fabric. You glance at the clock, it ticks. Another second, another breath, another invisible wobble in the fabric you now realise isn't so stable after all. But here's the thing you're starting to suspect. Your second might not be my second. And if we were moving differently, or standing at different altitudes, our seconds would get out of sync like 2 clocks falling out of rhythm. That's not a glitch, that's reality. Time, once believed to be the one universal constant, like a loyal friend always showing up in the same way for everyone, is actually a bit of a diva. It stretches, it slows, it speeds up, depending on where you are and how fast you're going. Time, it turns out, is local. Let's say you're standing on Earth watching an astronaut zip by in a fast-moving spaceship. To you, her clock is ticking slower. Her heartbeat, her aging, even the way she listens to music, it's all playing in slow motion. But from her perspective, you're the one being sluggish, stuck on your rotating planet while she zooms free through space. This is not an illusion. It's not some kind of perspective trick. It's how space-time works. Time is warped by both gravity and velocity. Einstein's special relativity covers the velocity part. The faster you move, the slower time runs for you, from someone else's viewpoint. You're still moving along normally in your own experience. It's only when you compare clocks that the weirdness shows up. General relativity then brings gravity into the mix. The deeper you are in a gravitational well, say, near a massive object like Earth, the slower time moves for you compared to someone higher up. Now, before you start blaming space-time for every time you're late to something, let's be honest, it's not making that much difference in your everyday life. But our satellites? Oh, they feel it. Take GPS. Those little machines orbiting above your head rely on precise timing to pinpoint your location. But guess what? Their clocks run slightly faster than the ones on Earth, because they're further from our planet's gravity. Not correcting for this difference would mean that your GPS coordinates would drift by about 10 kilometers per day. That would turn take the next left into drive off this cliff. So yes, time dilation is very real, and technology literally has to account for it just to help you find the nearest Thai restaurant. Here's a wild thought. Your head ages slightly faster than your feet. You're experiencing more time at your scalp than at your toes, because your head is ever so slightly farther from Earth's centre. Not enough to brag about, but it's there. Now back in the day, this would have sounded like absolute nonsense. When Galileo dropped things off towers, he assumed time was the same for everything. Newton followed suit. Time was the great metronome of the universe. But in 1971, an experiment called the Haffel-Keating experiment threw all that under the Spacetime bus. Scientists took 4 atomic clocks and flew them around the world on commercial airliners, 2 eastward, 2 westward. When they returned, they compared them to clocks that stayed on the ground. And yep, they were out of sync. Not because the clocks malfunctioned, but because they experienced time differently. Depending on their altitude and speed, some clocks had ticked slower, some faster, exactly as Einstein predicted. Of course, most of us don't walk around worrying about time being stretchy. Your phone alarm still goes off when it should, but zoom out, or speed up, or fall into the right gravity well, and suddenly time becomes a negotiable thing. And here's your quirky fact for tonight. In 1935, physicist Paul Dirac once suggested that maybe the speed of light, and therefore the very fabric of space-time, might change over time. We now mostly disagree with that idea, but it's a reminder that nothing in science is sacred. Even the constants get side-eyed from time to time, and historians, they still argue whether Einstein fully grasped the implications of his own equations at first. His math said strange things about how time and gravity interacted, but some say he didn't believe those results were physical until much later. Like many geniuses, he might have had to catch up with his own work. So what does all this mean for you, lying in the soft glow of a screen, wondering how time could possibly be anything but normal? It means that your version of now is not universal. There is no absolute present in the universe. Someone on a distant planet, say, orbiting a star in Andromeda, has their own timeline, and their now might not line up with yours in any meaningful way. The further apart 2 events are in space, the fuzzier the idea of simultaneity becomes. You can't say, this star exploded at the same moment I was making toast, and have that be a meaningful, objective truth. Space-time doesn't allow it. What feels like a steady, reliable tick-tock is actually an illusion born from your size and speed and place in the cosmos. You're like a fish in calm water, unaware that the current even exists, until someone points out the drift. And that's the wild part. All this bending and stretching and time dilation weirdness. It's not separate from you. It is you. Your atoms obey these curves. Your heartbeat ticks along a local slice of time, obedient to the warps and swells of the universe's fabric. So the next time you check the time, remember that what you're really checking is your location in the fabric. And maybe, just maybe, that time is a little different than mine. You're not moving. At least that's what it feels like. You're curled up wherever you are, under blankets, sprawled on a sofa, possibly upside down like a sleepy bat. And everything seems still. But that stillness? It's just a local lie your senses are telling you. Zoom out far enough and you're not only moving, you're being stretched. That's right. The entire universe is expanding, and you're being taken along for the ride, whether you bought a ticket or not. Here's the twist though. While the cosmos is growing, you, your body, your house, your cat, are staying the same size. You're not inflating. Your atoms aren't spreading apart. Your coffee cup isn't slowly turning into a bathtub. Why? Because gravity, electromagnetism, and other local forces are strong enough to hold things together, even as space-time expands around them. This is one of the weirder things about our reality. It's called metric expansion, a fancy term for the way space itself stretches over time. Not things moving through space, not galaxies flying apart like glitter from a dropped craft project. The space between them is getting bigger. Imagine dots on a balloon. As you inflate the balloon, the dots drift apart, even though they're not moving relative to the surface they're on. That's how galaxies behave in an expanding universe. They're not flying away from each other because of motion. They're being carried apart by the growth of space-time itself. And here's where it gets uncomfortable. There's no outside of the balloon. That balloon isn't growing into anything, it's just getting more balloon. Likewise, space isn't stretching into something else. It's just stretching endlessly, internally. You might say the universe is the only fabric that can tailor itself without scissors or thread. This whole idea kicked off in earnest in the 1920s, when Edwin Hubble noticed that galaxies were redshifted. That is, their light was stretched toward the red end of the spectrum. That's the cosmic version of hearing a siren drop in pitch as it speeds away from you. The farther away the galaxy, the more redshifted it was. That meant the universe was expanding. QMass, existential panic, and champagne, possibly at the same time. Now here's a quirky tidbit for your pillow talk. Georges Lemaitre, a Belgian priest and physicist, actually beat Hubble to the punch. He proposed the expanding universe idea 2 years earlier, using Einstein's own equations. But history tends to remember the telescope guy more than the theologian with a chalkboard. Historians still argue whether Lemaitre got snubbed or just shrugged, and let the credit slide in the name of humility. In any case, once expansion was on the table, people naturally wanted to know what's expanding, and more importantly, how fast. The answer is sneakily simple and mind-melting at the same time. Locally, nothing expands. Your molecules are bound tight by electric forces. The Earth isn't inflating like a sad beach ball. Your lungs are expanding because of muscles, not space-time. But once you zoom out to intergalactic scales, that's where the stretch shows itself. Between clusters of galaxies, far enough apart that gravity doesn't lock them together, the universe is growing. Distances are increasing. Not because the galaxies are moving, but because the ruler you'd use to measure them is swelling quietly. This is why distant galaxies aren't just redshifted by their speed. They're redshifted by the fact that the light they emitted has been travelling across expanding space. By the time it reaches you, it's literally been stretched. Like trying to shout across a trampoline while someone's pulling on both ends. Let's say light left a galaxy 1 billion years ago. That light's wavelength was a certain size when it began the journey. But as it travelled, space itself expanded, dragging the light like taffy, stretching the wavelength longer. That's why the farther a galaxy is, the more stretched, and redder its light becomes. And now, the terrifying cherry on top. The expansion isn't slowing down, it's speeding up. You'd think, with all that mass out there, galaxies tugging on each other, gravity doing its thing, the universe's expansion would gradually wind down, like a good toddler tantrum. But no, something, somewhere, is pushing the whole cosmic fabric faster. The gaps are growing quicker by the day. We call this mysterious force dark energy, but that's like naming your fear spooky stuff, and pretending that counts as understanding. We'll properly meet that unsettling character later, but for now just know that it's like someone added espresso shots to the universe, and then walked away without leaving a note. And here's the kicker. At a far enough distance, galaxies are already moving away from us faster than the speed of light. But wait, you might say, blinking sleepily, isn't that illegal? Nope. Because it's not the galaxies moving through space faster than light, it's space itself expanding. General relativity says that's allowed. The cosmic speed limit only applies to objects within space, not to space itself doing acrobatics. Which brings us to another odd moment. In a few trillion years, light from galaxies outside our local group won't be able to reach us anymore. Not because it's too far away, but because the space between us will have stretched so much, so fast, that light can't catch up. The stars will vanish, and future civilizations might think the universe is just a quiet bubble of darkness. That's not a science fiction scenario, that's an actual forecast. And speaking of forecasts, did you know that the ancient Greek philosopher Anaxagoras suggested that the sun was a huge flaming rock far away rather than a fiery god? Not exactly cosmic expansion, but a step toward realizing the universe was far bigger and stranger than it seemed. Historians still argue whether his insights were suppressed by politics or just ignored out of sheer confusion. So what can you do about all this expanding fabric? Absolutely nothing. You're along for the ride. You can't feel it. You can't stop it. But you're inside it. Always. The couch beneath you, the pillow under your head, the air in your lungs. It's all resting on a cosmic grid that's stretching with every passing second. The vastness is growing while your personal space remains blessedly unwarped. You're local. The universe is not. And somewhere out there, light is still on its way toward you. Its message distorted by a journey across a fabric that never holds still. You roll slightly, just enough to get comfortable, and the universe obliges, silently warping a little beneath you. Now, you've probably seen it before, that famous classroom demo where someone stretches a rubber sheet across a frame, drops a bowling ball in the middle, and rolls a marble near the edge. The marble spirals in, caught by the dent in the sheet. See? The instructor says. That's gravity. That's space-time curvature. And they're not wrong. Mostly. But let's be clear. The rubber sheet model of space-time is a double-edged sword. It's clever, iconic, and helpful, but also totally misleading if you take it too seriously. It's like using a cartoon to explain quantum mechanics. You'll get the gist, but the details? Those are another dimension altogether, literally. First, the good. The rubber sheet gives you a visual metaphor for what mass does to space-time. Big things make deep dents. Smaller objects roll toward them, following curved paths. Not because of a force, but because the straightest route on a curved surface is no longer, well, straight. It's intuitive. It's satisfying. And it makes people say, aha! But here's the issue. In that classroom demo, the ball curves the sheet because of gravity. You know, the very thing we're supposed to be explaining. The bowling ball only makes a dent because Earth is pulling it downward. The marbles only spiral in because they're also falling. Again, thanks to gravity. So we've just explained gravity using gravity. Not ideal. Real space-time curvature doesn't need a gravitational field pulling from below. The mass itself creates the curve. Gravity is the dent, not the reason for it. There's no cosmic flaw below the universe making things fall. That's where the metaphor starts wobbling like a cheap folding chair. And then there's the issue of dimensions. The rubber sheet is two-dimensional. The dent goes downward into a third spatial dimension. But real space-time isn't embedded in some higher space. It's self-contained. The curving doesn't happen in a direction we can point to with a ruler. It's more like a mathematical twist in the rules for how time and space behave around mass and energy. Imagine being a two-dimensional ant crawling across that rubber sheet. You'd feel yourself speeding up or slowing down, turning unexpectedly. You wouldn't see the dip, you'd just feel the results. That's how we experience space-time curvature. We're inside it. We don't see the warp. We live the warp. Still, the metaphor endures. Probably because brains like visuals, even if they lie a little. And who doesn't love a dramatic marble spiral? Let's add a quirky layer. In the 1800s, before Einstein was even a twinkle in the void, a German mathematician named Bernhard Riemann laid the groundwork for curved spaces. He didn't even need the universe to do it. He just wondered, hey, what if geometry doesn't have to be flat? That simple shift gave us the math Einstein would later use to describe gravity. Historians still argue whether Riemann truly grasped how deep his math would go, or whether he just wanted to mess with triangles for fun. And while we're deconstructing metaphors, let's talk about gravity's direction. You feel it pulling you down, right? Your butt on the mattress, your drink on the table, Your pet doing that loaf of bread thing in total defiance of physics, but from Spacetime's point of view, nothing's pulling. Instead, everything's following the natural path through curved space. Those paths, called geodesics, are the straightest possible lines in a bent reality. When you drop your phone, it's not falling because something yanked it downward. It's just following the shortest route through spacetime. Downward, yes, but only because Earth has sculpted a well in the grid, and your phone was sitting too close to the edge. Even your orbit around the Sun. Not the result of a tug of war, but the natural motion of an object travelling in a curved space. The same way a marble loops around the dent in a sheet, except, again, without needing to fall into a third dimension. But here's where things get really trippy. Time curves too. The rubber sheet model doesn't show this. It leaves out the most critical part, because gravity doesn't just bend space, it bends time. The closer you get to a massive object, the more space-time stretches downward, like a slow-motion vortex. Time literally runs more slowly near massive bodies. Stand at sea level and you age a little more slowly than someone standing on a mountain. Live your whole life at the top of Everest, and you'll rack up a few extra nanoseconds of existence. Not enough to make you immortal, but just enough to make your body a slightly better witness to the weirdness of time. And it's not just theory. Atomic clocks have proven this. Take two perfectly synced clocks, leave one on the ground and fly the other in a plane. When you compare them later, they disagree. One's ticked more than the other. Time is personal. Time is topography. It's not something flowing through space-time. Time is part of the fabric. So the next time someone shows you that demo with the rubber sheet, smile politely. It's cute, it's useful. But it's also like explaining love with a colouring book. Close enough to feel right, but nowhere near deep enough to reveal the truth. Here's a cheeky detail for your brain to chew on as you drift. Physicists have tried to come up with better metaphors than the rubber sheet. One favourite involves embedding space-time diagrams in higher dimensional spaces, but most of them require at least 4 cups of coffee and a nap afterward. There's also the famous embedding diagram of a black hole, those funnel-shaped wells you see in textbooks, which is just another 2D cheat pretending to show 4D geometry. Sometimes, even geniuses need a whiteboard and a cartoon funnel. At the end of the night, you don't need to abandon the sheet. Just don't marry it. Know that the real universe is weirder, deeper, and harder to visualize than a sagging square of fabric. Mass bends time. Curved time redirects motion. And the floor you think you're lying on isn't solid. It's part of a shifting, bending, silent ocean you're floating inside. No one ever said reality would be simple. But hey, at least it stretches nicely. You're falling. Don't panic. You're always falling. It's just that you've been doing it so smoothly, so continuously, that it feels like standing still. But the truth is, you're gliding down a slope in space-time, forever rolling through the curved geometry beneath your feet. You didn't trip. You were nudged by mass, by energy, by the subtle dip in reality Earth creates just by existing. This is gravity. Or more precisely, this is how gravity feels from inside the fabric. You're not being pulled to Earth. You're following the straightest path through curved space-time, what physicists call a geodesic. The trick is that straight path curves downward in space because of the way mass bends the grid. You're just obediently riding the rails of the universe. Right now, as you lie there listening, the Earth is stretching space-time downward into a gravitational well. You're sitting, lounging, possibly melting into your pillow, inside that dip. Not hovering above it, not pulled into it. In it. Held in place not by a force, but by the shape of reality itself. Let's get vivid. Picture space-time like a weirdly patient bedsheet that responds to mass. Drop Earth into it, and the fabric dimples. Toss in the moon, and it swirls gently in the curvature, not because it's being reeled in like a fish, but because it's tracing the most natural path in this dented landscape. What feels like an orbit is just constant falling, but with sideways momentum. The moon wants to go forward, but the curve in space-time keeps bending its path inward. so it dances in circles. It's Newton's apple with a horizontal kick. And here's the delightful brain bender. If the Earth suddenly disappeared, don't worry, it won't, but also maybe keep a towel handy just in case. The moon wouldn't feel it immediately. Because the shape of space-time takes time to adjust. The gravitational change would ripple outward at the speed of light, just like any other disturbance in the fabric. That's how intimately tied gravity and space-time are. You can't change one without changing the other. Now here's a quirky historical note. Long before Einstein, the ancient Indian astronomer Aryabhata in the 5th century proposed that Earth rotates on its axis, and that this rotation is what causes objects to fall toward it. Not exactly general relativity, but a surprisingly modern intuition, considering he didn't have satellites or laser interferometers, just math and a sky full of stars. Historians still argue whether his ideas influenced later Islamic and European thought, or were quietly forgotten for 1,000 years. Fast forward to now, and we understand that the pull of gravity is actually just an illusion caused by your resistance to free fall. Let me explain. If the floor suddenly vanished beneath you, you'd fall, obviously. But in that moment, you'd no longer feel your weight. You'd be in free fall, weightless, even though you're still under the influence of gravity. It's not the gravity that makes you feel heavy. It's the floor pushing back against the path you naturally want to follow. This is Einstein's equivalence principle, one of his favourite ideas. It says that the experience of gravity and the experience of acceleration are indistinguishable. If you're inside a sealed spaceship and feel yourself pushed into the floor, you can't tell if it's because you're accelerating through space or because you're parked on a planet. To you, it feels exactly the same. Gravity, then, is just the geometry that makes freefall feel like acceleration when you resist it. If you stopped resisting, if you let yourself fall, you wouldn't feel gravity at all. Want an example? Astronauts in orbit. They're not floating because there's no gravity. That's a common myth. There's plenty of gravity up there, about 90% of what we feel on Earth's surface. They're floating because they're falling. Constantly. They move sideways so fast that as they fall, Earth curves away beneath them. It's the most graceful faceplant in the universe. Now think about this. The same curve that holds the moon in orbit is what keeps your feet on the floor. It's all geometry. Space-time is one enormous invisible slide, and everyone's riding it. Let's pull back even farther. Think about Jupiter. Big, beefy, full of attitude. Its gravitational well is much deeper than Earth's, which is why time ticks slower there. And near a black hole, time practically stands still. That's the ultimate dip in space-time, a region so warped the fabric folds in on itself. We'll get there soon, promise. But for now, let's stay on Earth. You may not feel it, but your body is in tension. The ground is pushing up on you constantly, matching the downward slope of space-time you're trying to follow. Your atoms are mildly annoyed by this, buzzing with resistance. That push, that normal force, is why your legs don't sink through the floor. It's also why your thighs hurt after standing too long. You're resisting the most natural motion in the universe, free fall. This also means that when you drop something, a spoon, your phone, your self-esteem, it's not being pulled by a force in the traditional sense. It's being allowed to follow its path. Gravity doesn't push, it doesn't pull, it guides. Let's round things out with a strange but real-world twist. Engineers designing roller coasters or airplane flight paths have to think about perceived gravity, the G-forces. But those forces, they're not gravity at all. They're the result of your body being accelerated against its preferred path in space-time. A loop-the-loop on a roller coaster presses you into the seat not because of gravity, but because the track is forcing you to deviate from the natural fall your body wants to experience. In that moment, you're feeling geometry. So next time you're sitting still, remember, you're not at rest, you're in denial. Your body's trying to fall along a curve and the planet is rudely interrupting. You're falling. You've always been falling. And in a universe made of curves, that's the only way to stay in one place. You feel it before you hear it. A low ripple. Not a sound exactly, More like a hum stitched into the bones of the cosmos. It's not coming from anywhere, it's through everything, through you. You probably missed it. Everyone did. Even though it passed straight through your body, your house, the trees outside, and the crust of the Earth itself. It warped space-time by a fraction of a proton's width and then kept going, like a ghost brushing past in the night. This is a gravitational wave, born from the most violent events the universe can stage, black hole collisions, neutron star mergers, maybe even echoes from the Big Bang itself. Gravitational waves are the proof that space-time is not static. It isn't a frozen grid or a lifeless canvas. It's flexible, elastic, it wiggles, and tonight you get to ride one. Now it took humanity a while to catch these waves. For decades, they were ghosts predicted by math. Elegant, but unreachable. Then came a machine so precise, so absurdly sensitive, that it could measure changes thousands of times smaller than an atom. That machine is called LIGO, the Laser Interferometer Gravitational Wave Observatory. It works by sending lasers down 2 4-kilometre-long vacuum tubes set at a right angle. The beams bounce off mirrors, recombine, and cancel each other out perfectly, unless the length of one arm changes. And what could cause that? A passing gravitational wave, slightly stretching one direction while squeezing the other. In 2015 it happened. 2 black holes, each over 30 times the mass of the Sun, spiraled into each other more than 1 billion light-years away. They slammed together in a finale that warped space-time hard enough to be heard, or at least felt. LIGO picked up the ripple, and just like that, Einstein's century-old prediction was confirmed. And the waveform, it chirped, literally, a faint whoop in the data, like a champagne cork popped across time. It wasn't just a technical victory, it was cosmic eavesdropping. We'd opened a new sense, a gravitational ear to listen to the fabric itself. And that fabric has been whispering ever since. Now here's a quirky blast from the past. In the 1960s, physicist Joseph Weber built the first devices intended to detect gravitational waves. They were massive aluminum cylinders called Weber bars, and he claimed to have seen signals. Most physicists now agree those detections were optimistic, but he deserves credit. He was the first person to try to hear the universe in this way. Historians still argue whether his work was fruitless or just too early. So what exactly is a gravitational wave? It's not sound. It's not electromagnetic radiation like light or radio. It's a ripple in the geometry of space and time itself. It compresses and stretches the distance between objects, ever so slightly, as it passes through. And you can't shield yourself from it. You can't hide. When one passes by, it affects everything, because it's not moving through space. It is space. You're not in a room that shakes when a wave hits. You are the room. Here's something wild. The wavelength of a gravitational wave from colliding black holes can be hundreds, or even thousands, of kilometers long. It's like the universe is ringing with bass notes so low they'd rattle planets if they were audible. And what's most deliciously strange? These waves travel at the speed of light. Gravity has no delay. When something massive jiggles hard enough, space-time itself carries the message across the cosmos with perfect punctuality. So let's rewind. 2 black holes orbit each other. Close. Tight. Their immense masses bend space-time so sharply that time near them slows to a crawl. As they dance, they stir the fabric, sending out ripples. The dance gets faster, tighter, louder. In the final seconds, they spiral into each other, smashing together and collapsing into a single spinning monster. The ripple from that event doesn't fade quickly. It radiates outward for billions of years, barely losing strength, until one day, today, it washes through Earth, through you, through your blanket, your walls, your bones. You didn't notice. Of course you didn't. But it happened. And it's not just black holes. Neutron stars, those city-sized balls of crushed matter left behind after a supernova, can also collide. When they do, They light up the sky and sing spacetime's deepest tones. One such event in 2017 gave us gravitational waves, gamma rays, visible light, radio signals, and more. It was the first time we saw and heard the same cosmic event. Multi-messenger astronomy. Sounds like a superhero team, and honestly, it kind of is. Here's a fun twist. Gravitational waves can't be blocked or scattered. They move through matter like it's not even there. That means they can carry information from places that light can never escape, like the very edge of a black hole merger or the earliest moments of the universe, when everything was too dense and hot for photons to move freely. So if we want to hear the Big Bang itself, gravitational waves might be the only messenger old enough to still be humming that tune. But for now, we mostly listen for black holes. You might think space is quiet, empty, still, but it's not. It's vibrating with ancient ripples, and now we have the instruments and the patience to catch them. Want a trippy afterthought? Every time a gravitational wave passes through Earth, the entire planet subtly changes shape, not in any way you'd feel. But if you measured the diameter of Earth during a wave's passing, you'd find it slightly squashed. Not just Earth, the solar system too. Space-time itself momentarily deforms. Then, like a shaken sheet returning to stillness, it smooths out again. Quiet, pretending nothing happened. But you know better now. You've heard the whisper, you've ridden the ripple, and somewhere in the dark, two monstrous black holes are spiraling toward each other right now, making space-time sing again. You stretch your limbs slightly. Not much, just enough to feel the fabric of your blanket move around you. But something else is stretching too, all around you, beyond your ceiling, past the clouds, farther than the furthest star you've ever made a wish on. The universe. It didn't start stretching gently. Oh no. It began with a sprint so absurd it still makes physicists wince a little when they say it out loud. We're talking about inflation, the fastest growth spurt in the history of anything, anywhere. In the first sliver of a second after the Big Bang, less than a trillionth of a trillionth of a trillionth of a second, the universe went from subatomic speck to something you could see with the naked eye, if you'd had eyes back then. Which you didn't, because eyes hadn't been invented yet. But if they had been, you would have seen space ballooning outward faster than the speed of light. Yes, faster than light. How is that allowed? Because remember, it wasn't stuff moving through space. It was space itself expanding, and space is under no obligation to obey speed limits. This period is called cosmic inflation, and it's responsible for ironing out a lot of the wrinkles in our universe's early formation. Before inflation, space was probably a chaotic mess, like a toddler's crayon drawing of a fire truck during an earthquake. But inflation smoothed it out, stretched it, made the cosmos large, flat, and eerily uniform. It's like shaking out a wrinkled bedspread by hurling it into the stratosphere. But what triggered it? That's the great mystery. One idea is that a weird high-energy field, called the inflaton field because physicists are excellent at naming things, drove the expansion. This field had potential energy stored in it, and for a brief moment, that energy acted like a kind of negative pressure, forcing space to blow up like a startled balloon. Then, like a party guest who eats all the cake and disappears before cleanup, the inflaton decayed, dumping its energy into particles, heat, and radiation, giving us the Big Bang as we usually picture it. So yes, technically the bang came after the stretch. Here's a strange little detail for your trivia vault. The idea of inflation was first proposed in 1980 by physicist Alan Guth. He was trying to solve a problem with magnetic monopoles, a kind of hypothetical particle that, if real, should be everywhere, yet isn't. Inflation was his accidental solution. He found the math before he found the interpretation. Historians still argue whether inflation was a happy accident or an inevitable step in cosmology's evolution. Either way, inflation explains a lot, like why the universe looks mostly the same in every direction, cosmic microwave background we're looking at you. or why space seems so flat instead of curved and tangled. Without inflation, we'd have a lumpy asymmetrical universe with galaxies leaning like drunk dominoes. But here's the uncomfortable part. We don't really know what caused inflation, or even if it definitely happened. The evidence is indirect. The math works beautifully, the predictions fit our observations, and it ties up a lot of loose ends. But that inflaton field, we've never seen it, never touched it. It could be an elegant myth. Still, cosmic inflation remains one of the most popular ideas in modern cosmology. It's like the prequel to the Big Bang, explaining the part of the movie that starts before the opening credits. After that initial chaotic burst, the universe didn't stop expanding, it just calmed down, like a toddler finally tiring out after a sugar rampage. The expansion continued at a more reasonable pace. Matter began to cool, particles formed, atoms clung together. Light was finally able to travel freely, and ever since the universe has been doing its best impression of a very slow balloon, expanding steadily, 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 but not always at the same speed. See, there were growth spurts, times when the universe was too hot, too cold, or too crowded to expand evenly. The first stars switched on and pumped out radiation. Galaxies formed. Clumps of matter started gathering like anxious introverts at a party. This clumping actually slowed down expansion for a while, gravity trying to rein things in, pulling against the stretch. But then, a few billion years ago, something changed. Expansion started speeding up again. Cue ominous music. This second acceleration, the one happening right now, is thought to be caused by dark energy, which we'll curl up with in a later section. For now, just know this. The universe, after a long awkward phase full of gas clouds and puberty stars, is now back to growing faster. Not as fast as inflation, but fast enough to make your local galaxy cluster feel a little isolated. Which brings us to a philosophical musing. When people say the universe is expanding, what do they mean? It's not like there's an edge of space flying outward into a big blank nothing. Space isn't expanding into anything. Instead, the very metric that defines distance, the invisible coordinate grid of the universe, is stretching. Galaxies aren't rushing away from each other in the normal sense. The space between them is growing. If you could pause time and measure the distance between two unbound galaxies today, then again, 1 billion years from now, the distance would be larger, even if neither galaxy had moved at all. It's like marking 2 dots on a rubber band. Stretch the band and the dots move apart, not because they're moving, but because the thing between them is changing. And guess what? That rubber band is getting stretchier with time. But don't worry, this isn't something you feel locally. Your body, your chair, your cat's very judgmental stare, none of them are expanding. Electromagnetic forces, chemical bonds and gravity keep small-scale things tightly knit. The cosmic expansion is only noticeable on the bigger scales. The gaps between galaxy clusters, the long, slow drift of light from the distant past. So tonight, as you lie there still and small and warm in your local gravity well, the rest of the cosmos is swelling quietly beyond your reach. Light from the youngest galaxies is getting redder, cooler, fainter, stretched thin by the very space it travels through. And somewhere out there, inflation's final echo is still ringing. Softly, persistently, like a lullaby played on the edge of time. The sky above you is quiet, too quiet. Not in the spooky movie sense, but in the grand existential way. Because if space is expanding, stretching, rippling like some invisible dough, it begs a question you've probably asked at least once in your life, possibly while staring at the stars or while trying to fall asleep after a documentary binge. What is the universe expanding into? It's a natural question. If the fabric of reality is stretching, surely it's stretching into something, right? Some kind of bigger, blanker space? A void around the void? A backstage area for reality? Sorry to disappoint, but no, there is no outside. Not in any conventional sense. The universe isn't a balloon expanding into a room, it's the room itself getting bigger. There's no edge, no border, no cosmic wall to lean on and peer over. The expansion is happening within space itself. The distances between things are increasing, but not into anything else. Let's go back to that balloon analogy, because yes, we're using it again. It's flawed but useful, like every good metaphor in science. Imagine the surface of a balloon, not the inside, not the outside, just the two-dimensional surface. If you draw dots on it to represent galaxies, then inflate the balloon, you'll see the dots drift apart as the surface stretches. Now here's the catch. From the perspective of a creature living on that surface, one with no access to the third dimension, there is no centre of the expansion. Every point sees every other point moving away. And there's no edge. The surface is finite but unbounded. That's what our three-dimensional space might be doing. Expanding, yes, but not into anything. Just more of itself. It's a difficult concept because our monkey brains evolved to navigate trees and not abstract manifolds. We're hardwired to think in terms of stuff inside other stuff, but space-time doesn't play by those rules. Here's your quirky brain snack for the night. In the 14th century, French bishop and philosopher Nicolas Oresme argued that space might be infinite and centreless, an idea that got him a few strange looks and probably fewer party invitations. Historians still debate how close he was to modern ideas about the universe, but the fact that medieval thinkers were already flirting with infinity, that's impressive. Now you might still be wondering, if there's no centre and no edge, how did the universe start? That's the really fun part. The Big Bang wasn't an explosion that happened at a point in space. It happened everywhere, all at once. Every point in space was once compressed into a hot, dense state. And then, poof, space itself began to expand. So you're not watching the fireworks from the sidelines. You're in them. You're part of the original burst. Every atom in your body was once packed into a universe the size of a grapefruit, or smaller. Possibly much smaller. You're not in the aftermath of the Big Bang, you're in the middle of it. Still happening, still stretching. And here's the trippy follow-up. If the universe is infinite now, it was probably infinite then too. Just incredibly hot and dense. The Big Bang wasn't the birth of space from nothing. It was the rapid expansion of an already existing fabric. A fabric with no boundary, no outside, and no centre to point to and say, there, that's where it started. There is no centre of the universe. Let that one sink in while you readjust your pillow. Wherever you are right now, that is the centre. And so is every other point in space. Because in an expanding, homogeneous, isotropic universe, every place looks like the middle. Every observer sees galaxies moving away in all directions. You're not special, but neither is anyone else. It's the fairest geometry you can get. Now here's something science fiction often gets wrong. Forgive them, they mean well. The idea of reaching the edge of the universe. You can't. Not because we haven't tried, but because it doesn't exist. The universe isn't a spaceship you can exit. It's more like a video game map that keeps generating terrain no matter how far you walk. But there are limits to what we can see. Because light takes time to travel, there's a maximum distance from which light has had time to reach us since the Big Bang. That distance defines our observable universe, a bubble about 93 billion light-years across, filled with everything we've had a chance to glimpse. That's not the whole universe, that's just the part whose light has arrived. Outside the bubble, possibly infinite space, more galaxies, more stars, maybe even wildly different physics, though that's still speculative. And here's where things get philosophical. If we can't ever reach beyond the observable edge, if the light from those far-off places will never reach us because the expansion of space is too fast, can we say they exist? Are they part of reality? Or just ghost chapters in a book we can't open? Cosmologists love this question and hate it, because the answer is maybe. It depends how you define real, and in a universe made of stretching fabric and disappearing horizons, that definition gets slippery fast. One more mindbender for your nightlight thoughts. There are models of the universe where space is finite but unbounded. That means it loops back on itself like the surface of a sphere. If you could travel in a straight line far enough, you'd end up back where you started, like a cosmic Mario Kart track with no edges. You'd never hit a wall, but you'd repeat the scenery eventually. So, is space infinite, or is it finite but looping? Historians still argue whether early cosmologists were too quick to assume an infinite universe, or too afraid to admit they had no idea. Modern data leans slightly toward flat and infinite, but honestly, we're still figuring it out. What we do know is this: the stretching never stops. There's no outer rim, no blank waiting room that space is expanding into. It's just space-time, expanding on its own terms, writing its own rules as it goes. You're drifting inside a universe with no edge and no outside, a place that makes more room for itself as it grows. Not bad for a fabric made of equations. And somewhere just beyond the horizon of what you can see, the stretch continues, soft, silent, and endlessly strange. You shift slightly, maybe pull the blanket a little tighter. Outside your window, or above your head, or just beyond the last blink of a familiar star, there's a glow that's been there since the beginning. You can't see it, not with your eyes, but it's there, faint, cold, persistent. It's the whisper of the Big Bang itself, the cosmic microwave background, or CMB for short, and it's the closest thing we have to a baby picture of the universe, a long exposure snapshot of the cosmos when it was only 380,000 years old, which, in universal terms, is barely out of diapers. What makes the CMB special isn't just how old it is, it's what it tells us about the early stretch marks of space-time, because hiding in that faint background glow are tiny, tiny irregularities, wrinkles, variations in temperature and density so small they're measured in microkelvin. And those tiny bumps, they're the reason galaxies exist. Let's rewind, because you're sleepy and time is imaginary. At first, the universe was hot. Not just summer in Florida hot, unfathomably hot. It was a plasma of free-floating particles, protons, electrons and photons all bouncing around, slamming into each other, trapped in a kind of soupy chaos. Light couldn't move freely. Photons just kept colliding with particles like a pinball machine with no drain. But as the universe expanded, it cooled. That stretch we talked about in earlier sections didn't just increase the size of space, it also lowered its temperature. Eventually, things calmed down enough for electrons to bind with protons and form neutral atoms. That changed everything. Suddenly light could travel freely, the fog lifted. This moment is called recombination, and the light released then has been travelling ever since. It's the oldest light in the universe, stretched out over billions of years by the expansion of space. What began as high-energy radiation has now cooled into microwaves that are everywhere. And when we finally learned to detect them in 1965, accidentally, by two radio engineers named Penzias and Wilson, who thought they were hearing pigeon droppings in their antenna, we discovered the most important echo in history. At first, the CMB looked uniform, a warm beige glow wrapped around the sky. But then scientists built better telescopes. Instruments like COBE, WMAP, and Planck began to reveal the truth. It wasn't uniform at all, it was lumpy. Tiny fluctuations, imperfections, like goosebumps on the skin of the cosmos, and those lumps were the seeds of structure. Regions where matter was just a little denser than average. Gravity got to work, pulling in more matter, creating stars, galaxies, clusters. The entire cosmic web, all the beauty you see in the night sky, grew from those primordial wrinkles. Now here's your quirky historical nugget. Soviet physicist Yakov Zeldovich predicted these fluctuations decades before we had the instruments to see them. He was often overshadowed by flashier figures, but many of his ideas laid the foundation for modern cosmology. Historians still argue whether he deserves more credit for anticipating, what became some of our deepest discoveries. And those fluctuations, they're not random. Their scale, shape, and distribution match the predictions of inflation theory almost perfectly. The pattern of bumps in the CMB is like a fingerprint left by the earlier stretch of the universe, the Big Bang's messy signature on the wall of time. But here's the part that will make your pillow feel just a bit smaller. That light, the CMB, isn't coming from the edge of the universe. It's coming from every direction equally, because the universe is filled with it. You're inside the sphere. You're always at the centre of your observable CMB, just like everyone else. The light has been redshifting, stretching for nearly 14 billion years just to reach you, right now. And that stretching, that's key. The wavelengths of those photons have lengthened with the expanding universe. They started as visible and infrared light, but now they're microwaves. Cold, low-energy signals barely above absolute zero. The CMB's current temperature, about 2.725 Kelvin. That's colder than liquid helium. That's the thermal echo of everything smeared out across all of space-time. And those stretch marks, those faint temperature variations, aren't just static, they're structure. They map the earliest topography of the cosmos. They tell us where matter clumped, where it didn't, where the universe started to define its shape. It's the universe's oldest feedback loop. Now, not everything about the CMB is fully understood. Some anomalies, like the so-called cold spot, a region slightly cooler than expected, have sparked debate. Is it a statistical fluke, a sign of a super void, or, cue the dramatic music, evidence of a multiverse? Historians of science still argue whether we'll ever resolve these oddities, or if future generations will come to see the CMB as only part of a much larger cosmic picture. Here's something else to consider. We won't always be able to see it. Eventually, the universe's expansion will redshift the CMB so much that it will fade into undetectability. The sky will grow colder, darker, emptier. Future civilizations, assuming they exist and are smart enough to invent science instead of just social media, might never know the CMB was ever there. To them, the universe will look still and empty. No cosmic background, no echo of a bang, just silence. But you live in the golden era of cosmology. The universe still speaks to you. Its earliest light still bathes you, softly, silently, like a whisper from a past that never entirely faded. And when you close your eyes, you are surrounded by it, submerged in a light older than stars, dimmed not by time but by stretching. The most ancient whisper, made longer by the fabric of space as it expands beneath you. So the next time someone tells you space is empty, remind them it's glowing, quietly, constantly. And written in that glow are the first stretch marks of reality. So, the universe is expanding, not just from the Big Bang, not just coasting gently, like a balloon drifting upward after a birthday party. It's speeding up. Let's pause and appreciate how weird that is. Everything we know about physics tells us that when something explodes, it starts fast and then slows down. That's what gravity does. It reins things in. It's the universe's ultimate buzzkill. You'd expect the Big Bang to fling matter outward, and then gravity, ever the party pooper, would gradually pull things back or at least slow the pace. But that's not what's happening. Instead, galaxies are flying away from us faster than they used to. The gaps between them are growing more rapidly with time. The universe isn't slowing down, it's flooring the accelerator. What could be doing that? Enter dark energy, the universe's least understood, most powerful ingredient. It's invisible, ungraspable, and unreasonably chill about the fact that it makes up nearly 70% of the cosmos. Dark energy isn't a particle. It's not a gas, a fluid, or a wiggly quantum thing, probably. It's more like a property of space itself, an intrinsic quality of the vacuum that causes it to push outward. Yes, you heard that right. The vacuum is pushing. This is not the vacuum cleaner kind of vacuum. It's the space between galaxies kind. The empty part of the universe. The places where there's no matter, no radiation, no neutrinos, no clutter at all. Just space. And yet, even there, dark energy lives, quiet, passive-aggressive, unfathomably strong over time. Now here's where it gets technical and dramatic at the same time. In 1998, 2 independent teams of astronomers were studying supernovae, those big stellar explosions that help us measure cosmic distances. They expected to find that the expansion of the universe was slowing. Instead, they discovered something utterly baffling. Distant supernovae were fainter than expected. That meant they were farther than they should have been. That meant the expansion had sped up since those stars exploded. Cue the dramatic music, cue the champagne, cue the "wait, what?" from every theoretical physicist alive. And just like that, the idea of a smooth, slowing universe was replaced with something much weirder. A cosmol being torn apart by something no one could see. Here's your quirky historical note of the night. Einstein himself once introduced a cosmological constant into his equations to stop the universe from expanding or contracting. He thought the universe should be static. When it turned out the universe was expanding, he called the constant his greatest blunder. But in a delicious cosmic twist, the cosmological constant might actually be real. Not to keep the universe still, but to make it stretch faster. Historians still argue whether Einstein would have considered that a redemption arc or just further proof that the universe has a mean sense of humour. So what is dark energy? The honest answer is, we don't know. One leading theory is that it's the cosmological constant itself, an unchanging energy built into space, present at every point in the universe, pushing outward evenly. But some theories suggest dark energy could vary over time, that it might be connected to quantum fields, that it could decay, or reverse, or even, wait for it, rip the universe apart. That's not hyperbole. There's a model called the Big Rip, where dark energy becomes so dominant that it eventually overwhelms everything. Galaxy clusters, galaxies, solar systems, planets, molecules. It would tear atoms apart. Spacetime would unravel at the seams. But don't worry. That's a few tens of billions of years away. Plenty of time to finish your tea and read a few more bedtime cosmology scripts. Right now, dark energy isn't shredding anything. It's subtle, gentle, but it's relentless. It's the reason distant galaxies are receding from us faster and faster. Not because they're moving through space faster than light, which would break the rules, but because space itself is expanding between us and them. And since that expansion is accelerating, there's a weird, sad side effect. Some galaxies are already moving away from us faster than their light can reach us. That means they're effectively gone. Their light will never get here. Not now, not ever. They've crossed what we call the cosmic event horizon, a kind of point of no return, beyond which light emitted now will never reach Earth, no matter how long we wait. And as time passes, more galaxies will slip past that horizon. The observable universe is shrinking, not in size, but in content. We're losing access to parts of the cosmos, quietly, inevitably, permanently. It's like being in a room where the walls aren't closing in, but the doors are vanishing. And one day, far in the future, only our local group of galaxies will remain visible. Everything else will be gone too far, too fast beyond the grasp of light. Future astronomers might believe they live in a lonely universe. They'll look at the sky and see only the Milky Way and its closest neighbours. They won't know what we know now. They won't see the echo of the Big Bang. They won't know about the Great Stretch. Dark energy will have made their sky a lie. So, what can you do about this mysterious cosmic inflator? Absolutely nothing. And that's okay. You're inside the expansion. Part of it. Made of atoms that were born in galaxies now sliding into permanent darkness. You're stitched into the very fabric that's being pulled apart, slowly, silently. Tonight, as you lie there, warm, safe, perfectly unaware of the trillion-year future stretching out ahead of us, dark energy is doing its work. Not with drama, not with explosions, but with a pressure so small you can't feel it, and so vast it's shaping the fate of everything. You lie there in the quiet, surrounded by the steady ticking of now. At least that's how it feels. Seconds pass, one after the other. Maybe you check the time, maybe you don't. But beneath all that stillness, a very peculiar thing is happening. Or more precisely, not happening. Because now doesn't exist. Not the way you think it does. Not in the way that feels obvious. The way your brain wants it to be. One single, shared, universal moment that everyone everywhere is experiencing together like a big cosmic live stream. Nope. In the fabric of space-time, now is flexible, local, conditional. It stretches and warps depending on where you are and how fast you're going. There is no universal clock ticking in the sky, no master timeline coordinating every event in the cosmos. Your now is not my now. And neither of ours matches the now of a lonely particle drifting between galaxies. Let's dig into this, not with math, but with metaphor and sleepy wonder. In Newton's world, time was absolute. It ticked forward like a giant metronome in the void. Everyone, everywhere, moved along with it, like dancers hearing the same beat. That model worked beautifully for centuries. Then Einstein showed up and broke the clock. With his theory of relativity, time stopped being absolute. It became part of the fabric of reality, space-time, and that fabric bends and stretches depending on mass and motion, which means time itself bends and stretches too. And suddenly, simultaneity, the idea that two things can happen at the same time, no matter where they are, isn't a fundamental truth anymore. Two events that seem simultaneous to you, say, two fireworks exploding on opposite sides of a field, might not seem simultaneous to someone watching from a moving train. They might see one go off before the other, and both observers would be correct in their own frames of reference. This is called the relativity of simultaneity, and it's one of the most unsettling concepts in all of physics. It means that now is not a slice of the universe that exists all at once. It's more like a personal opinion. Depending on your velocity and gravitational environment, your version of what's happening now somewhere else can be completely different from someone else's, and both of you are right. This means there's no cosmic instant when everything, every star, every planet, every toothbrush and teacup and existential crisis shares a single moment. Time isn't one long movie we're all watching together. It's more like a patchwork of overlapping short films, each playing on its own slightly different schedule. Now here's a quirky historical footnote for your time-travelling brain. Einstein's friend and philosophical pen pal, Hermann Minkowski, was the first to formally describe space-time as a four-dimensional continuum. He once said, "Space by itself and time by itself are doomed to fade away into mere shadows." Historians still argue whether Minkowski fully appreciated just how weird his insight would become, or whether he accidentally launched the most unsettling metaphysics lesson in history. So what does it mean, really, that now doesn't exist universally? It means that the present isn't an objective slice of time carved across the cosmos. The present is relative, defined by your speed and your gravitational environment. Right now, someone moving quickly through space, say a particle zipping past Earth, experiences a different present than you do. They might already be in your future, or still in your past. There is no master timeline for the universe, no cosmic command center flipping calendar pages. Space-time is a four-dimensional fabric. Events are just coordinates, points in space and time. All of them exist, in a sense, in this grand structure. The past, the present, the future, they're not flowing like water. They're laid out like a landscape. You're not moving through time. You're within time. You occupy a location in it. And movement? That's an illusion created by your consciousness, which is built to perceive changes, not absolute coordinates. Let's try a mental image. Picture the universe like a loaf of bread. Each slice represents a moment in time, but the way you cut that loaf, your angle, your perspective, depends on how fast you're moving. Someone else, moving differently, slices the loaf at a different angle. Your slices are not the same, and so your now is not theirs. This leads to all kinds of uncomfortable implications, like your future might already exist, just not in your current slice. Or the past isn't gone, it's just in a different coordinate of space-time, inaccessible, but still there. These ideas lead directly into the block universe theory, a concept that treats time as just another dimension. In this view, past, present, and future all exist equally. Nothing flows, nothing fades, everything simply is, forever, in its place. In this model, you are a four-dimensional being stretched across space-time like a spaghetti noodle, experiencing one moment at a time because your brain is built to live that way. Spaghetti you. A time noodle with memories. Delightful. Of course, not all physicists buy into the block universe idea. Some argue that time really does flow, and that something fundamental about reality is lost when we treat all moments as equally real. Historians still argue whether the block model captures truth, or just gives our math a convenient filing cabinet for everything that's ever happened or will happen. But from the perspective of relativity, one thing is certain. Time is not global. It is not absolute. Now is not something the universe agrees on. So what's the practical takeaway as you listen to these gentle truths from the edge of everything? It means that every moment is more local than you thought, more personal, more fragile. Time is yours, not because you control it, but because it's shaped by the place you occupy in the universe, your heartbeat, your breath, the rhythm of your thoughts. These are your moments, your slices of the infinite loaf. They're not the same slices being experienced by a star 10 billion light years away. They might not even be in the same century. You're surrounded by time, not passing through it. And somewhere out there, right now, from your perspective, a galaxy is forming in what we would call the past. And somewhere else, a star is dying in what we call the future. But those are just different angles of the same bread. The cosmic clock doesn't tick, it just is. And you? You're a blink of space-time, here and gone, resting in your own personal slice of now. You fall, slowly, silently, and not in any way that hurts. You fall through time, through space-time, through the bend in reality itself. But now, tonight, you're going to fall farther, deeper, past the point where clocks break and geometry starts curling up like burnt paper. You're falling into a black hole, the place where space-time forgets what it's doing. Let's begin with something familiar: gravity. You've learned that gravity isn't a force pulling you downward, it's the slope of space-time, and black holes, they're where that slope gets so steep it becomes a vertical drop. A black hole is not a thing, it's a region, a place in space-time where the curvature becomes so extreme that not even light can climb out. It's the final, most dramatic expression of what gravity can do when you give it too much mass and not enough space. It doesn't pull, it just warps. And you're going in. Let's set the scene. You're orbiting a star that's about to die. It's massive, dozens of times the mass of our sun. For millions of years it's burned brilliantly, fusing hydrogen into helium, helium into carbon, and so on, until it runs out of fuel. Without pressure to hold up its own weight, the star begins to collapse. And it doesn't stop. The core compresses, gravity takes over, the collapse accelerates. In moments, it packs more mass than our entire sun into a space smaller than a city. The curvature of space-time spikes. The surface, if we can call it that, recedes behind an event horizon. This is the point of no return. You fall in. And what you notice first, if you're far enough from the singularity to still notice anything, is that time starts acting funny, not for you. Your personal clock ticks on normally, your heart beats, your thoughts drift, perhaps to snacks. But to an outside observer, your time begins to slow. From their perspective, you crawl toward the event horizon slower and slower until you freeze, motionless, just outside the edge. You never quite fall in. You just fade, your image redshifting, growing dimmer until you vanish. But from your point of view, you fall right through. You cross the event horizon, and nothing special happens in that moment. No alarm, no fireworks, no scream of violated physics. You don't feel the edge, but you've passed it. From this point onward, every direction in space leads you further inward, including the direction we used to call time. Inside a black hole, time and space swap roles. You can't stay still anymore, even in theory. Just like you can't stop moving through time in normal life, you now can't stop moving through space, inward. The singularity isn't a point in space. It's a moment in your future, one you can't avoid even if you try. And what is a singularity? It's the place where our equations break, where space-time curves to infinity, where mass is crushed into zero volume, where the very fabric of reality crumples under its own weight. We don't actually know what happens there. Our current physics, general relativity and quantum mechanics, have a nasty breakup inside black holes. They stop cooperating. General relativity says space and time bend infinitely. Quantum mechanics says, "Are you kidding me?" and throws a chalkboard out the window. This is the cosmic no-go zone. But let's linger a moment before you hit it. Let's talk about spaghettification. Yes, it's a real word. You can whisper it. It makes the situation feel better. If the black hole is small, say a few solar masses, the gravity gradient is extreme. That means your feet fall significantly faster than your head. You're stretched, pulled into a long, sad strand of atoms, like spaghetti. But if the black hole is supermassive, millions or billions of times the sun's mass, then the event horizon is enormous and the gravity gradient is gentle. You could fall through without even noticing. In fact, if you ignored the crushing final destination, you might call the ride peaceful. And here's your quirky fact for the night. The very idea of black holes was once dismissed as absurd. The term black hole wasn't even coined until the 1960s. Before that, physicists used phrases like frozen stars and dark stars. John Michell, an English natural philosopher, speculated about stars so massive that light couldn't escape back in 1783. Historians still argue whether he truly anticipated modern black holes or just got lucky with gravity. Let's add one more layer. Time. Inside a black hole, time itself ends. Not in the poetic, "wow, what a concept" way. Literally. Time reaches a boundary. This is hard to imagine. You've always existed inside time. Every breath, every blink, every memory is placed along a timeline. But here, inside the most warped geometry in the universe, there's a moment when there are no more moments. It's not that your clock stops ticking, it's that there is no after. You reach the singularity, and that's it. It's not death, it's not sleep, it's the terminus of time, the edge of before and after. The singularity doesn't live inside the black hole, it is the black hole, condensed into a finality we can't explain. This is where theory breaks. Some physicists believe singularities must be resolved by a theory of quantum gravity, a future model that unifies the smooth curves of relativity with the jittery probabilities of quantum mechanics. Maybe the singularity is avoided, maybe information is preserved, maybe time continues in a form we can't yet comprehend. But right now, the math goes dark, and you're still falling, or maybe you're already gone. From the outside, the black hole looks quiet, peaceful. No clue what's going on beneath the event horizon. It's the most polite chaos in the universe. No screaming, no flailing, just perfect darkness. But even that darkness speaks. Black holes can spin, they can charge, they can evaporate, slowly, through a process called Hawking radiation, where quantum effects near the horizon cause the black hole to lose mass, particle by particle. Over trillions of years, it may fade away entirely. What happens to the information that fell in? We don't know. That's the black hole information paradox, a puzzle that has tormented physicists for decades. If information is truly lost, it breaks the laws of quantum mechanics. But if it's not, how is it preserved? No one agrees. Some say it's stored in the event horizon. Some say it leaks out slowly. Some say the universe hides it in tangled strings of multi-dimensional math. Historians still argue whether black holes are cosmic erasers or misunderstood archivists, but one thing's certain, they mark the ultimate limits of stretch, the place where space-time bends so far that time itself gives up. And somewhere, far above, clocks still tick, galaxies still drift, microwave background radiation still hums its ancient tune, but not for you. You've passed the boundary where time dissolves, you've stepped into the fold, and even in that fall there is a kind of silence, a stillness not of death, but of being in a place where time itself no longer stretches. It simply stops. You made it back, or maybe you never left. In space-time, who can really say? Either way, let's shake off the singularity dust and crawl out of that black hole, because tonight, your sleepy little mind is going on a joyride. No falling, no collapsing, no infinite curvature or broken physics. This time, you're driving. Tonight you're going to warp space. Welcome to the dream of faster-than-light travel, or more specifically, faster-than-light illusion, because even in our most sci-fi moments, you're still shackled to the speed limit of light, unless you cheat. And cheating, in this case, means bending space-time itself. Cue the warp drive. The idea starts with a question that has kept scientists, writers, and probably more than a few overly enthusiastic conspiracy theorists up at night. If space-time can bend and stretch, could we shape it ourselves? What if, instead of moving through space at incredible speeds, we let space move for us? What if we could compress space in front of us and expand it behind, riding a wave of space-time like a cosmic surfboard? This isn't just Star Trek fan fiction. This is the Alcubierre drive, a real theoretical concept proposed in 1994 by physicist Miguel Alcubierre. His idea? Create a warp bubble around a spacecraft. Inside the bubble, the ship stays still, but the bubble itself travels through space-time by contracting the space ahead of it and stretching the space behind. You're not breaking the speed of light because your ship isn't moving through space faster than light. It's space that's moving around you. Clever, right? There's just one teensy-weensy problem. Actually several. First, to create this warp bubble, you'd need negative energy. Not just regular energy, but exotic stuff. Something that behaves opposite to everything we know. It's like asking for a car that runs on unicorn dust and bad vibes. In principle, negative energy can exist in quantum physics. Think Casimir effect. But to power a warp bubble, you'd need more negative energy than exists in the known universe. And second, it might destroy everything. Yeah, the original Alcubierre model would generate catastrophic radiation at the front of the bubble. Like, turn the destination planet into a microwave burrito levels of catastrophe. Not ideal. Still, researchers haven't given up. Later versions of the concept, like the Notario drive or more recent tweaks to Alcubierre's equations, try to reduce the energy requirements and fix the deadly side effects. Some even speculate that with enough quantum field manipulation, tiny warp effects might one day be possible. Tiny as in move a particle a little faster in a vacuum chamber, not take a nap on Alpha Centauri. But let's not get discouraged. Science fiction exists to stretch the imagination, and warp drives are the ultimate fantasy of making space-time work for you. It's the flip side of falling into gravity wells and black holes. Instead of being at the mercy of space-time shape, you shape it. You carve a path, you ride the fabric. And that leads us to another crowd favourite, the wormhole, another way to cheat distance by bending space-time not just along a curve, but by folding it and poking a hole through. Like folding a piece of paper in half and sticking a pencil through both sides, a wormhole connects two distant regions of space through a tunnel that shortcuts the stretch. In theory, you could travel light years in seconds. In reality, we've never seen one. We don't even know if they exist. The equations allow them. Einstein himself helped define them, calling them Einstein-Rosen bridges. But like warp drives, wormholes require negative energy to stay open. Otherwise, they collapse faster than you can say instant cosmic death. Still, they haunt the edges of physics, because if space-time is bendable, and mass can shape it, and gravity can curve it, then why not fold it so tightly that two distant points kiss? Some physicists believe that wormholes could be real, but microscopic, smaller than atoms. Others argue they could exist naturally in black holes, or as relics from the early universe. Some even say advanced civilizations could build them, but only if they've mastered physics so far beyond us, it might as well be magic. And here's your quirky gem of the night. In the 1980s, physicists Kip Thorne and Michael Morris actually wrote papers exploring how humans could theoretically travel through a wormhole without dying instantly. Their ideas were serious enough to inspire Interstellar, complete with Thorne consulting on the film's science. Historians still argue whether Thorne's contributions to sci-fi have educated or merely terrified generations of filmgoers. Back to warp drives. Why do we even want them? Because the universe is huge. Stupidly huge. Even light, the cosmic overachiever, takes over 4 years just to reach the nearest star. Getting anywhere interesting without breaking physics requires absurd patience or absurd cheating. So warp drives and wormholes give us an emotional loophole, a way to imagine not being forever confined to one tiny corner of the cosmic map. They let us dream that maybe, just maybe, we don't have to wait billions of years to visit the other side of the galaxy, and maybe dreaming is enough, for now. Because here's the real truth. Space-time can be stretched. We see it all the time. The universe does it constantly. But doing it on purpose? That's another level. We don't yet know how to generate the kind of precise, localized space-time distortions that a warp bubble or wormhole would require. But we do know that the equations allow it, which means the door isn't locked, just very heavy and very weird. So tonight, as you drift between dimensions of dreams and half-conscious thought, imagine it. Your ship hovering in stillness. The space in front compresses. The stars behind stretch into ribbons. You don't feel motion, because you're not moving. The universe is. And before you can blink, you're orbiting a distant star. A pale blue moon rises in the sky. You step out onto soft alien dust. And somewhere behind you, space-time curls gently back into place. You're drifting now, softly, suspended in the curved embrace of space-time, half asleep and still riding that warp bubble from before. But what if I told you the universe might have more dimensions than you can see? Not metaphorically, not metaphor in a wow, my dreams are so deep kind of way. I mean literally, physically. Dimensions curled up, tucked away, hidden in the nooks and crannies of reality like forgotten socks behind the cosmic dryer. Welcome to the wild theoretical world of extra dimensions. Let's start simple. You live in 3 spatial dimensions: length, width, height, and one time dimension. That's your standard 4-dimensional space-time cocktail. Everything you've ever known, touched, or dreamed about fits into those 4. But there are hints, subtle mathematical whispers, that our universe might be hiding more than it shows. The idea isn't new. In fact, it dates back to 1919 when physicist Theodore Kaluza tried to unify gravity and electromagnetism, 2 forces that seemed like they should be related. His trick: he added a 5th dimension, just one extra spatial dimension, hidden so tightly that you couldn't see it, but whose presence might explain how forces emerge. The idea was wild. Kaluza sent the paper to Einstein, who read it, paused, and then wrote back with his signature level of understated awe. He didn't fully understand it, but he didn't dismiss it either. Kaluza's idea evolved. Later, physicist Oscar Klein proposed that this extra dimension might be compactified, curled up in a tiny loop, so small that we can't detect it, even with our best microscopes. Think of an ant walking along a garden hose. From far away, the hose looks like a one-dimensional line, but if you get up close, really close, you see it's a cylinder. The ant can walk in 2 dimensions, forward along the hose and around its circumference. You're the ant. The universe might be the hose. You move through 3 big dimensions, but there might be tiny extra ones wrapped so tightly that you don't even know they're there. And then came string theory. Now, string theory is a mathematical behemoth, equal parts brilliant and controversial. It says that the fundamental particles of reality aren't zero-dimensional points, but tiny vibrating strings. The type of vibration determines what kind of particle it is: electron, photon, quark. Just different riffs on the same string. But here's the twist. String theory only works if the universe has 10 or 11 dimensions. That's not a typo. 10 spatial dimensions and 1 for time. The extra dimensions don't contradict what you see, they just hide. Like backstage crew in a play, they shape everything without ever taking a bow. According to the theory, 6 or 7 of those dimensions are curled up in intricate shapes called Calabi-Yau manifolds, complex higher dimensional geometries that make compactification look like origami on quantum steroids. And these tiny hidden dimensions, they influence the physics we do see. The way the strings vibrate depends on the shape of these curled up spaces. It's like the resonance of a violin string changing depending on the shape of the violin. So, the behaviour of every particle in your body might be shaped by the geometry of invisible dimensions you'll never touch. Comforting, right? Here's your quirky night fact. In 1995, physicist Edward Witten proposed a unifying theory known as M-theory, which extended string theory into 11 dimensions. It's still very much a work in progress. Historians still argue whether this mathematical move was a breakthrough or just another level added to an already complicated Jenga tower. Now, are these extra dimensions real? Maybe. We haven't detected them directly. But some researchers think we might one day find evidence. Perhaps through tiny deviations in the behaviour of gravity at small scales, or through high-energy collisions at particle accelerators that might reveal energy disappearing into a hidden dimension. In fact, some experiments have already tried to test this. The idea is that if gravity can leak into extra dimensions, it might explain why it's so much weaker than the other fundamental forces. Why can a fridge magnet beat the gravitational pull of the entire Earth? Maybe because gravity is diluted, spread across more dimensions than we can perceive. The Large Hadron Collider deep under the French-Swiss border has looked for signs of this. So far, nothing definitive, but the possibility lingers, and now we arrive at one of the strangest, most brain-tickling possibilities of all. What if the universe isn't just made of curled-up dimensions, but exists on a brane, a three-dimensional surface floating inside a higher dimensional space? This is the brane world scenario, and yes, the spelling is correct. Not brain, as in your sleep-soggy grey matter, but brain as in membrane, a concept from string theory, where our universe is like a slice of bread in a much larger loaf. We might be confined to our brain, unable to access the extra-dimensional bulk around it. Gravity might be the only force that seeps through. Other universes, other brains, could float nearby, just millimeters away in another dimension. Multiverse? Anyone? Suddenly, parallel universes aren't just philosophical ponderings. They become spatially adjacent realities, reachable only by crossing dimensions we can't even point to. But don't worry, you're not going to fall into one. These theories are beautiful, rich, and entirely unconfirmed. Yet, we might live our entire lives in 3 visible dimensions, unaware of the silent orchestra of extra spaces shaping the laws of nature. And here's the sleepy truth. Even if you never see a Calabi-Yau manifold or feel the gravity of another brain, your body is a sculpture shaped by these hidden dimensions. Your atoms hum because of vibrations that might be tuned by curled-up geometry. Your time flows forward because it has no other choice. And your dreams? Well, maybe they drift sideways, into spaces just a little too small to notice. You blink, or maybe you don't. It's hard to tell when your eyes are half closed and your brain is curling inward like a sleepy hedgehog. But even in this drowsy state, there's something moving. Not big, sweeping motions, not galaxies drifting or black holes swallowing. No, this motion is tiny, chaotic, jittery, impossible to pin down. It's space-time dancing at the smallest possible scale. Tonight we zoom all the way in, past atoms, past protons and neutrons, past quarks. We're diving into the deep end of reality's basement. Welcome to the realm of quantum fluctuations, where space-time isn't smooth, but grainy, restless, and endlessly weird. Let's start with the myth you've probably grown up believing, that a vacuum is empty. It's not even close. A vacuum, the kind you find in deep space or in a very expensive lab, isn't a true void. It's a quantum field party. Even when there's no matter, no light, no particles to speak of, the underlying fields that fill the universe are still there, and they are never at rest. These fields fluctuate, constantly. Pairs of particles and antiparticles pop into existence from nowhere, flirt briefly, then annihilate each other and vanish again. This doesn't violate conservation of energy, because these virtual particles exist only for the tiniest blinks of time. Quantum mechanics allows it, and the universe apparently takes full advantage. This jittery chaos is called vacuum energy, and it's everywhere. You, lying quietly under your blanket, you're hovering in a sea of quantum whispers. Space-time is never truly still beneath you. It's jittering, trembling, a storm measured in Planck lengths and Planck times, units so small they make atoms look like beach balls. At this level, the concept of space-time as a smooth fabric begins to fall apart. It's not a sheet. Is not even thread. It's more like foam, bubbly, frothy, ever-changing. This idea is known as space-time foam, first proposed by physicist John Wheeler in the 1950s. He imagined that at the Planck scale, roughly 10 to the negative 35th meters, space-time would be dominated by violent random fluctuations. Tiny wormholes might blink in and out of existence. Geometry might contort. The very topology of the universe might not be fixed. It's like a churning ocean made entirely of uncertainty. And here's your quirky fact of the night. Physicist Freeman Dyson once joked that if quantum fluctuations were a little stronger, you might spontaneously create a cow. The math says it's possible, just extremely unlikely. But technically, the universe could burp a cow into being and then unburp it a moment later. Comforting, right? Now, these quantum jitters aren't just theoretical noise, they have real, measurable consequences. The most famous is the Casimir effect. Place two uncharged, parallel metal plates extremely close together, just a few nanometers apart, and they'll actually attract each other. Why? Because the quantum vacuum energy between the plates is slightly less than the energy outside them. The imbalance creates a tiny pressure that pushes the plates together. It's one of the most surreal examples of nothing doing something. Another consequence? The Lamb shift, a tiny change in the energy levels of electrons in atoms due to vacuum fluctuations. It's been measured, confirmed. The vacuum isn't quiet, it talks. Now what happens when you try to combine this jittery quantum world with Einstein's serene, bendy space-time? You get problems, lots of them. Quantum mechanics and general relativity are both brilliant, both accurate, but they don't get along. When you try to apply quantum rules to the gravitational field, things spiral out of control. Your equations explode. Infinity starts showing up where it's definitely not invited. This is the infamous problem of quantum gravity. Physicists have been trying to unify the two theories for decades. String theory is one attempt, loop quantum gravity is another. Both try to explain how space-time behaves when you zoom all the way in, how it might be made of discrete loops or vibrating strings or geometric atoms of space and time. But none of these theories is complete. We're still fumbling in the dark. And speaking of dark, remember dark energy from before? The mysterious force causing the universe to expand faster and faster. Some scientists think it might be related to vacuum energy, the sum total of all quantum fluctuations throughout the cosmos. But when you actually do the math, the predicted energy of the vacuum is way too large, like 10 to the power of 120 times larger than what we observe. That's not a typo, that's a 1 followed by 120 zeros. This is called the cosmological constant problem, and it's the most embarrassingly wrong prediction in the history of physics. Historians still argue whether this represents a flaw in our understanding of quantum fields, a misunderstanding of gravity, or just a cosmic joke we haven't gotten yet. So here we are. inside a universe made of bendable space-time filled with invisible fields that never sleep, where energy flickers in and out of existence for no reason other than it's allowed. And those fluctuations, they may be the seeds of everything. Cosmologists believe that the tiny random quantum jitters during cosmic inflation, the ultra-fast expansion we talked about earlier, got stretched across the universe. They became the tiny differences in density that eventually grew into stars, galaxies, planets, cats, chairs, and you. You're, in a very literal sense, the large-scale consequence of microscopic randomness. You're cosmic static, so tonight, as you drift deeper into sleep, remember, the stillness you feel is a lie. Even in the quiet, even in the dark, the vacuum boils. Space-time jiggles. Virtual particles leap and vanish. And somewhere, at the very edge of theory, reality loops and tangles, whispering truths we haven't yet deciphered. You rest in the eye of a quantum storm. You breathe on a sea of fluctuations, and even nothing is something. You float now, quietly, not just through space, but on space, or maybe within space. You've learned by now that space isn't a stage, a backdrop, or an empty void. It stretches, it curves, it wrinkles. But tonight, let's ask a more daring question, one that doesn't get asked nearly enough. What shape is it? Not your room, not your town, not even the space between galaxies. We're talking about the shape of the universe itself, the full, all-encompassing geometry of space-time, the shape of everything. Seems like a simple enough question. But like most things in cosmology, the answer is somewhere between probably flat and we have no idea. Let's break it down. The universe can take on one of three basic shapes, at least according to general relativity and what we understand about geometry on cosmic scales. Flat, open, or closed. Picture it like this. A flat universe is like a sheet of paper that extends forever. Parallel lines never meet. Angles in a triangle add up to 180 degrees. It's Euclidean, comforting, straightforward, infinite, but not curved. A closed universe is like the surface of a sphere. Triangles have more than 180 degrees. If you keep going in one direction long enough, you eventually come back to where you started, like walking in a straight line on Earth and ending up behind yourself. It's finite but unbounded. An open universe is like a saddle. It curves outward. Triangles have less than 180 degrees. Parallel lines diverge. It keeps stretching forever and ever, getting more and more open. These are shapes not in three-dimensional space, but of space itself. The universe may be three-dimensional, but its curvature is baked into its structure, into how matter and energy bend space-time. So how do we know which kind we live in? We measure. Like the good little monkeys with telescopes that we are. We observe the cosmic microwave background. Remember that faint afterglow from the early universe? It carries the imprint of space's geometry. Tiny temperature fluctuations tell us how light travelled through the early universe and what kind of shape it had to move through. And right now, all measurements point to the universe being very nearly flat. Almost perfectly so. Not curved like a sphere, not warped like a saddle. Just flat. But almost is the key word. Because the universe is so enormous, possibly infinite, we can only measure the part we can see. The observable universe. That's the bubble of space whose light has had time to reach us since the Big Bang. Roughly 93 billion light-years across, give or take a few eternities. If the true universe is much bigger, and there's every reason to believe it is, then even a slightly curved shape might appear flat to us. Just like standing in a small clearing on Earth might convince you the planet is flat because you can't see the horizon bend. It's like trying to judge the shape of a trampoline while sitting on a single spring. Now here's a quirky historical twist for tonight. In the early 20th century, Russian mathematician Alexander Friedmann derived solutions to Einstein's equations that included all three possibilities: flat, open, and closed universes. Einstein initially dismissed the non-static ones, wanting the cosmos to be eternal and unchanging. Historians still argue whether Einstein's resistance delayed cosmological progress or simply gave other thinkers like Georges Lemaitre room to shine. So what does the shape of the universe mean for the future? Glad you asked, because now things get dramatic. If the universe is closed, gravity might eventually overcome expansion. Everything would slow, stop and reverse in a fiery collapse known as the Big Crunch. Galaxies would race inward, stars would collide, and space-time itself might collapse into a singularity. Cue ominous soundtrack. If the universe is open, it would expand forever. Galaxies would drift apart until their light could no longer reach each other. Stars would die. Black holes would evaporate. Everything would fade into cold, dark silence, a scenario lovingly called the heat death. If the universe is flat, its fate depends entirely on what's in it, especially how much dark energy is hanging around. And based on current data, we're headed toward forever. Not a crash, not a loop, just endless accelerating expansion, a lonely, freezing, starless end to everything. Don't worry though, you've got at least a few 100 billion years before things get bleak. That said, not everyone agrees. Some theorists have proposed even weirder fates like the Big Rip, where dark energy increases over time until it tears apart galaxies, stars, planets, molecules, atoms, and eventually space-time itself. Everything gets ripped to shreds by the very fabric that once held it together. Others suggest a bounce model, where the universe expands, collapses, and then re-expands in a cycle of bangs and crunches. Some versions even hint that black holes in one universe could create new universes on the other side. Physics, it seems, has a taste for reincarnation. Still others argue we may live in a bubble universe, one of many in a multiverse of differently shaped and governed realities, some open, some closed, some shaped like cosmic pretzels for all we know. It's like trying to guess the shape of the ocean from inside a single drop of water. But here's a calming thought to fall asleep with. The shape of the universe doesn't change how cozy your corner of it can be. It may be infinite, it may loop back on itself, it may stretch forever or someday pop like a cosmic soap bubble. But your stars still shine, your clocks still tick, your blanket's still warm. You live on a tiny branch of a vast and curious geometry, and whatever the ultimate shape may be, you are held in it, safe, snug, and surrounded by curves too vast to comprehend. So go ahead, drift a little further, float on the flatness. Let the gentle slope of space-time cradle you. You're part of the shape, and the shape somehow includes you. Time, until now, has been your gentle companion. It ticks along second by second, whispering memories in one direction and possibilities in another. You've accepted its rules. No skipping ahead, no rewinding. Always forward, always one step at a time. But tonight we're going to bend that rule. You're going to flirt with the forbidden. Because if space-time can stretch, fold and ripple, could it also loop? Could you travel through time? Time travel isn't just science fiction. It's science's unruly younger sibling, the one that crashes the party, eats all the cake, and demands answers no one wants to give. But here's the surprise. Physics doesn't entirely forbid time travel. In fact, some solutions to Einstein's equations allow it. The math permits closed time-like curves, paths through space-time that bend so thoroughly they loop back on themselves. You start at one point, and arrive at that same point earlier, like walking a long, twisty path that eventually leads you to your own front door the day before you left. Let's begin with the concept that started it all, the Gödel universe. In 1949, mathematician Kurt Gödel, yes, the same one who proved math has holes in its logic, used Einstein's equations to construct a model of the universe where time travel was possible. It involved a rotating universe, spinning so hard that space-time itself twisted into loops. You could travel in a spaceship and end up arriving before you left. Gödel's universe isn't our universe. It doesn't match our observations, but it was the first formal proof that relativity allows time travel, at least in theory. Other models followed. The most famous, the wormhole, a shortcut through space-time connecting two distant points. If one mouth of the wormhole is accelerated to near light speed and then brought back, time inside it will pass more slowly. Thank you, relativity. This creates a time difference between the ends. Step through one mouth and you emerge before you entered. But there are problems. Big ones. Wormholes aren't just theoretical, they're delicate. They require negative energy to stay open. We talked about that back in the warp drive section. Negative energy isn't something you can pick up at the corner store, it's theoretical, exotic, and possibly unstable. Then there's the paradox problem. If you go back and change something, like stopping yourself from inventing the time machine, what happens? Does reality break? Do you vanish? Does a new timeline split off? Do you just get a headache and go home? This is the infamous grandfather paradox. What happens if you go back and prevent your own existence? One possible answer: you can't. Something always stops you. The gun jams, the time machine malfunctions, you get distracted by a sandwich, the universe protects itself. This idea leads to the Novikov self-consistency principle, which basically says events in space-time are self-consistent. If time travel occurs, it can't change events in a way that causes contradiction. You might go to the past, but you can't change it. Whatever you do was already part of history, a little grim for free will, but tidy. Other physicists embrace the chaos. They propose the many worlds interpretation, the idea that every quantum event spawns a branching universe. Go back in time and kill your grandfather. Congratulations, you've just created a new timeline where you don't exist. The original one, still chugging along, unaware of your meddling. In this view, time travel doesn't change the past. It just kicks off a new one. And here's your quirky historical gem. In 2009, Stephen Hawking hosted a party for time travelers. He sent out the invitations after the party happened, just to test if anyone from the future would show up. No one did. Probably because they were busy, or polite, or more likely because time travel into the past is extremely unlikely, even if not strictly forbidden. But forward time travel? That's very real. You're doing it right now, and you could do it faster. Einstein's relativity guarantees that time passes more slowly the faster you move, and the stronger the gravity you're in. Want to visit the future? Board a ship that travels near light speed, or hang out near a black hole, mind the event horizon. When you return, everyone else will have aged more than you. That's not theory, it's fact. Astronauts on the ISS age microseconds less than people on Earth. It's tiny, but measurable. Time travel to the future is already built into your GPS, but travelling backward, that's still a dream. A maybe. A math trick in search of reality. And even if we figured it out, should we? Imagine a machine capable of punching holes in time. What could it do? What would we do with it? Historians still argue whether the very possibility of time travel breaks causality. That beautiful chain of cause and effect that keeps our lives from spiralling into narrative mush. If time is a river, time travel is a rock thrown into it. The ripples echo forward and backward. Maybe it smooths itself out. Maybe it floods everything. Either way, space-time doesn't offer easy answers, just open loops, which brings us to the final twist. Maybe time isn't a line, maybe it's a circle, or a loop with frayed ends, or a spiral that never quite doubles back but always rhymes. You live in a reality where clocks tick forward, but the laws of physics don't seem to care which way time flows. The equations work the same in reverse. It's only entropy, the rising disorder of systems, that gives time its arrow. Maybe time only feels one way because your memories do. Maybe everything is still there, past and future, tucked into the fabric of the universe like grooves on a record. You just can't lift the needle. So tonight, as your breathing slows and your thoughts begin to drift, imagine a version of you who made different choices. Maybe they're out there. Maybe they're just ahead. Or maybe if you turned around quickly enough, if you curve space-time just right, you could catch up with yourself, past you, future you, all stitched into one endless fabric. You've bent time, you've curved space, you've ridden waves, dodged paradoxes, and peeked behind the curtains of causality. But now it's time to ask a darker question, one that even space-time seems a little afraid to answer. Can it break? Not warp, not wrinkle, not just stretch like cosmic taffy. We mean snap, tear, shatter. What happens when the fabric of reality doesn't just flex, but fails? Welcome to the unsettling world of space-time singularities, cosmic censorship, and the apocalyptic concept of the Big Rip. Let's start with what we know. Space-time is astonishingly sturdy. It's been twisted by black holes, stirred by gravitational waves, and inflated by dark energy. And yet, so far, it holds together. But there are moments, cracks, where our equations predict disaster. We met one already. The singularity inside a black hole. A point of infinite density, where space-time curves so sharply it effectively turns into a knot. A place where the known laws of physics go to die. At least that's the story general relativity tells. But is it a real place? Or just the mathematical equivalent of dividing by zero? We don't know. The equations say, here be dragons. This is why physicist Roger Penrose proposed the cosmic censorship conjecture. The idea that singularities are always hidden behind event horizons, safely sealed away from the rest of the universe. Nature, he argued, censors these breaks in space-time. She covers them up so no one can see the mess inside. But here's the chilling part. We're not sure that's always true. There are solutions to Einstein's equations that allow for naked singularities, raw tears in space-time with no horizon to hide behind. Places where predictability fails and causality shivers in the corner. Some of these solutions are highly unstable, which is comforting, but some might not be. Then there's the question of topology change. Can the fabric of space-time actually rip and reconnect? Some physicists say yes, in rare and extreme scenarios. Others argue that quantum gravity would step in and stop it. But right now, we don't know what that quantum version of space-time looks like. If it's smooth, if it's digital, if it has seams. What we do know is this. If space-time has a breaking point, dark energy might be the thing that finds it. Let's talk about the Big Rip. It starts off subtly. The universe is expanding as usual. Galaxies drift apart. Then the expansion speeds up, and it keeps speeding up, and keeps, and keeps. Eventually it gets so fast that galaxy clusters can't hold together. Gravity gives up. Galaxies themselves are torn apart. Stars fly loose. Then planets. Then atoms. Molecules unbind. The bonds that hold matter together, even the strong nuclear force, are overcome by pure geometric stretch. In the final moments, space-time expands so violently that it tears itself apart. The coordinate grid breaks, the math collapses, time itself ends. This is the Big Rip. We don't know if it's real. Current data suggests that dark energy is a cosmological constant, steady over time. But if it's not, if dark energy grows stronger, this apocalyptic ending becomes possible. And here's your quirky, unsettling bedtime fact. Some models of phantom dark energy, yes, that's what it's called, suggest the Big Rip could happen as soon as 22 billion years from now. That gives you some time to prepare, maybe pack a snack. Now, what does it mean for space-time to tear? It's not just a visual metaphor, it's a failure of geometry, a place where distances stop making sense, where you can't say how far apart 2 points are, or even whether time can pass between them. It's not just destruction, it's undefined. In mathematics, we call this geodesic incompleteness, the technical way of saying that there are paths through space-time that just end. No edge, no boundary, just a sentence with no period. In other words, a rip. And not all rips are catastrophic. There are hypothetical models where baby universes bud off from ours, space-time pinching off like a cosmic soap bubble. These could be white holes, theoretical opposites of black holes, or quantum tunneling events that create new inflating regions of space. Some versions of inflation theory suggest this is how our universe started. born from a rupture in some parent universe, which means our entire cosmos might be someone else's tear. Historians and physicists still argue whether this model is too speculative to take seriously or too elegant to ignore. After all, if spacetime can split, why wouldn't it have done so before? This brings us to the cutting edge of speculation, spacetime as emergent. What if spacetime isn't fundamental? What if it's just a large-scale illusion, like temperature or pressure, emerging from the collective behaviour of something deeper? Quantum entanglement, information, holography. In this view, you don't tear spacetime the way you tear cloth. You break it the way a network crashes, at the level of connection. Some researchers believe that entanglement, the quantum link between particles, might be the true fabric. That spacetime is built from entanglement. If the entanglement structure changes enough, spacetime itself could disappear. Not break, just cease to exist. There's even a saying in quantum gravity circles, ER equals EPR. It's a wild idea suggesting that wormholes, Einstein-Rosen bridges, and entangled particles, Einstein-Podolsky-Rosen pairs, are the same thing, which means spacetime might be woven from quantum threads. Pull the wrong thread, and the whole thing unravels. But let's bring it back to you, lying there, breathing steadily, floating on a patch of spacetime that, so far, has not snapped. Your galaxy still holds together. Your planet spins quietly. Gravity works. Time moves forward. The math, for now, holds. But somewhere, deep in the void, equations tremble. Somewhere the fabric stretches a little too far, and maybe, just maybe, it whispers back, I can break. You've stretched across the cosmos, not in body but in thought. You felt the ripples of black hole mergers, glided through warped space-time, peeked into curled-up dimensions, drifted past collapsing stars and rising horizons. You've touched the oldest light in the universe and whispered hello to time loops, phantom energies, and the edge, if there even is one, of everything. And now, you settle back into yourself, because we've reached the quiet centre of this entire wild, stretching story. You. What does all this bending, twisting, expanding fabric of space-time mean for you? For the human curled under a blanket, listening to cosmic bedtime tales? Here's the strange answer. It means more than you think. Because you aren't floating on top of space-time. You're made of it. Every atom in your body obeys its rules. Your time passes not in spite of the universe's stretch, but because of it. Your thoughts unfold along a path carved into curved geometry. The neurons firing right now are doing so inside a moving, humming, expanding grid of space and time. And more than that, you're shaping it. Yes, you. Your body bends space-time, and not much, granted. You're not going to lasso any comets with your gravitational pull, but technically, mass equals curvature. Just by existing, you leave a tiny dent in the cosmic sheet. Your presence changes the geometry of the universe, however minutely, and so does every other mass, every planet, every drop of rain, every cat snuggled into a ball with its paws over its face. We're not passengers on the fabric, we're stitches in it, and that fabric has been stretching since before there were planets, before there were atoms, before time, as we understand it, even made sense. That stretch defines everything. Why galaxies drift apart, why light takes time, why there's a past to remember and a future to dream about, why the night sky is full of things we'll never reach, but can still see. We live in an expanding story, written in space-time, one stretch at a time. But it's also personal. Your sense of time, your heartbeat, your days, your memories, flows along a local slice of space-time unique to you. Your present moment is yours alone. And yet, it connects, softly, gently, to every other now in the universe. That means that right now, as you lie still, the universe is still moving. Space-time expands between distant galaxies. Gravitational waves ripple quietly through your room. Microwave photons from the Big Bang drift gently past your bed. And in the farthest corners of space, light from stars that died billions of years ago is just now reaching Earth and your eyes. It's all part of the same stretch, and it's still happening. In the time you've listened to this script, the observable universe has grown by a few hundred kilometers in every direction. Not because galaxies moved, but because space-time made room. And that's kind of beautiful, because no matter how complex the physics gets, no matter how many dimensions we uncover or how many paradoxes we chase, the truth remains. You're here, alive, brief, glorious. A flicker of self-awareness wrapped in molecules forged in stars strung together by biology, living briefly in a pocket of curved, stretching space-time. And when you look up at the night sky, you're not looking out, you're looking in, at a story you're part of, at a structure that holds you, at a stretch that began before you and will continue long after you're gone. But for this moment, for this breath, you're part of it. You are it. And whether the universe ends in heat or ice, in rip or rebound, the stretch of space-time has made room for you. So stretch out a little, exhale, let your limbs go heavy. Let the pull of Earth's gentle curvature cradle you. You've ridden the fabric, you've explored the warp, now rest in the ripple. Because everything is stitched together by this same silent weave, and even in the dark, it holds.